Welcome to the Williamson ether synthesis lab. Here's the outline for the video. I'll be going over the reaction and the procedure and talking about the safety concerns for one of the reagents in this reaction. And then I'll go over phase transfer catalyst for a little bit and show the experiment in the lab. Here's the reaction that we'll be doing. We'll be taking 4-ethylphenol and reacting it with methyl iodide in an SN2 mechanism to form the ether product. This product is also known as anise, which is used in licorice flavoring. So as the product forms throughout the reaction, it'll smell something like black licorice. Now, phenols aren't great nucleophiles. It's not going to backside attack the methyl iodide on its own, so we'll be using NaOH to activate the phenol so that it becomes a good nucleophile. The problem is when the NaOH reacts with the phenol, the deprotonated phenol will move into the aqueous layer where the methyl iodide won't follow. And so we need a way to get these two reagents to interact and to react with each other to form the product. One way to do this is to use a phase transfer catalyst, and in this reaction we'll be using Tetrabutylammonium Bromide. And what a phase transfer catalyst does is it helps move reactants between phases. And it's able to do this because it can be soluble in both an aqueous and an organic phase. So if we take a look at tetrabutylammonium bromide, we can see large organic groups coming off of the molecule, allowing it to be soluble in an organic solvent, but the charged ionic center allows it to be soluble in the aqueous phase as well. Here's how it works in the mechanism. In the bottom half we have the aqueous layer where sodium hydroxide has deprotonated the phenol and formed the phenolic ion. And on the top half we have the organic layer with the other reagent, the methyl iodide. As the phenolic ion interacts with the phase transfer catalyst, what the solvent's mainly going to see is a bunch of organic groups, so both of those compounds will move up into the organic layer where the phenolic ion can then backside attack the methyl iodide and form the anise product. Then the remaining halide salt will migrate back into the aqueous phase, and this same process will repeat itself over and over again. To allow this process to fully happen, we'll allow the mixture to react for an hour at a temperature not to exceed 65 degrees Celsius as the methyl iodide refluxes. In order to monitor this, we'll place the conical vial in a hot water bath and measure the temperature of the water using a thermometer. Now, when setting up the reaction, we want to be really careful with methyl iodide. It's a known carcinogen, and if you look at the table at the safety issues, you can see it's corrosive, and it's a carcinogen because it methylates DNA. So when adding it to the conical vial, it'll be dispensed in the hood using an automated pipette, and we'll make sure to keep the cap on the container whenever we're not using the methyl iodide. Once the reaction is complete, the product ether layer on top can be removed and the remaining aqueous layer extracted 3 times with ether. Then the extracts will be rinsed with some sodium hydroxide to help remove any unreacted phenol that might have been left over from the reaction. Those extracts will be dried with sodium sulfate and then the ether solvent evaporated. Here we'll be careful not to evaporate the product as well, which shouldn't be an issue because its boiling point is 195 degrees Celsius, but oftentimes students get used to having solid products and evaporate all of the liquid off, but we don't want to do that this time because our product is going to be liquid as well. The product can then be purified using a dry silica gel plug, which will look like this, and we'll use methylene chloride as the mobile phase to elute the product out, gathering about 5 to 10 milliliters of that methylene chloride solution. Then the solvent can be evaporated and the product characterized by running an IR spec and measuring the refractive index. Alright, I'm going to start by adding 150 milligrams of 4-ethylphenol into a 5 milliliter conical vial and dissolve that in 250 microliters of 25% sodium hydroxide. This initially creates a really sticky mess, so I'm going to help stir it with a spatula until the spin vane can spin on its own and everything is dissolved in that solution. Then I'll add 15 milligrams of tetrabutylammonium bromide, which is the phase transfer catalyst. And finally, 90 microliters of the methyl iodide, making sure to keep the cap on the bottle whenever the methyl iodide is not being used and dispensing it with an automated pipette. Now I can set up the apparatus and start warming up the water, measuring the temperature of that water with a thermometer And I want to keep it somewhere in between 55 and 65 degrees Celsius. If it ever gets too hot, I can just add a piece of ice to cool down that water bath, and I'll let the reaction go for about an hour. Once the hour has passed, I'll remove the conical vial from the hot water bath and start getting some diethyl ether to begin the extractions. It's difficult to see the product ether layer, so I'm going to add some initially just so we can see it better, and remove the spin vein, rinsing it with some ether as well. Then I'll mix the phases together really well, and I'm actually going to add a little bit of distilled water to dissolve the remaining slurry and so we can see the phases better. Now I can remove the ether layer and continue to extract the aqueous one 3 more times with diethyl ether. Once the extractions are completed, I'll rinse the extracts with some sodium hydroxide to help remove any unreacted phenyl that might be left over. And I'll mix those 2 layers together really well to allow the base to interact with everything. And then I added a little bit of distilled water just to distinguish the 2 phases a little bit better. Then I can remove the basic phase and rinse the organic extracts with a little bit more distilled water to remove any excess base that might have been left over. Now I'll move the ether solution over to an Erlenmeyer flask where I can dry it using sodium sulfate, and I'll add that until it is free flowing. Once it is free flowing, I can remove the solution from the Erlenmeyer flask, and then to reclaim more product from the sodium sulfate, I'll go ahead and rinse that again with some more diethyl ether. Now I can evaporate the solvent with a stream of air and gentle warming and start setting up the dry silica gel plug. So I'll add a piece of cotton in the bottom at first. Then a little bit of Ottawa sand just to cover the surface area of the pipette. A couple inches of the activated silica gel. And just a little bit more Ottawa sand on top. Once the solvent has been evaporated off, I'll add 250 microliters of methylene chloride and transfer that solution now to the silica gel plug. I'll be using methylene chloride to elute the plug, and I can use a bulb to help push that through. But I'll be gathering about 5 to 10 milliliters of the methylene chloride solution in a separate conical vial. Once that has been gathered, I can start evaporating the solvent using a stream of air and gentle warming again until the liquid doesn't seem to be going down any further, meaning that it's just product. Now I can weigh the full conical vial for the percent yield and run a neat IR to see how pure the product ended up. Unfortunately, there's a little bit of OH contamination, possibly from the phenyl reagent left over, but other than that, it looks pretty good. We have the 2 carbon-oxygen peaks for the ether group, one at 1250 and the other at 1036. Finally, I'll measure the refractive index, so I'll place some of the product onto these crystals, and then looking through, I'll place the line separating the light and dark hemispheres right through the crosshairs, and look at the index given. It's a little higher than literature value, but it's still pretty dang close. Now at the end, I'll weigh the empty conical vial to calculate the mass of product obtained, and that is it for this reaction.